Good morning, myself Nancy from BSc Chemistry Honors first year making video on chapter solid state. The solid state under classification. A solid state is defined as a form of matter which possesses radicity and hence poses a definition shape and a definite volume. The solids are divided into two types, namely called crystalline and amorphous. Crystalline solid. A solid is said to be a crystalline if the virus ion and atom molecule of which are solid is made up of the arrangement in a different geometrical pattern. All the solid elements and the compound exist in this form, and the crystalline solid are further classified into a number of types, which has been discussed in section 3.23 along with the example of each type. Amorphous solid. Amorphous solid. A solid is said to be amorphous if the constituent ion, atom, and molecule of the substance are not arranged in any regular fashion. Although the possessively resistively defined shape and defined volume, glass, pitch, rubber, polymer of the higher molecular mass, in fact, the amorphous substances are not regarded as a true solids. Rather, they are considered to be highly supercolloidal liquid to be very high viscosity. Point of difference between the crystalline and amorphous solid. First, the arrangement of particle in a crystalline solid. The constituent particles are arranged in a definite geometrical pattern, whereas in an amorphous solid they are not arranged in any regular fashion. Second, melting point. The crystalline substance possesses a sharp melting point, whereas amorphous solid substance melt gradually over a temperature range. Isotropic and anisotropic. In the case of amorphous substances, the property like the electricity, conductivity, refractive index, thermal expansive are the identical to all the direction. Like in the case of gases and liquid, the property is called isotopic, and the substance showing this property is called isotopic. On the other hand, in the case of crystalline solid substance, the property maintain about the different value and difference direction, and this type of behavior is called the anisotropic, and the substance exists this type of behavior are called the anisotopous, whereas the amorphous solid are where the amorphous solid substance are the isotropic in nature, and the crystalline substance are anisotropic. The anisotropic is just by the crystalline substance is observed due to the fact that the measurement of different direction and different type of particle fall in on a way and shown in the figure 3.1, or the arrangement of particle is different. Regular or irregular cut. A crystalline of a solid is being a cut in a sharp as a knife give a clean and cleavage, whereas an amorphous solid undergo irregular breaking as shown in figure 3.2. Cooling curve. When a molten crystal is cooled and temperature is plotted against the time, the cooling curve is obtained by he has break at a point where the solidification start and where the solidification is completed. The heat evolved during the solidification keep the temperature constant, and cooling of a melted amorphous solid give a smooth cooling and curve and break. The main point of the difference between the crystalline and amorphous solid may be summarized as follows. Tux to Tux to see the given solid is a crystalline in nature is must be exist the flowing character. First is possessive of a defined geometry. Second, possessive of sharp melting point. Third, existence of anisotropic, and fourth, should be give a clean cleavage. Classification of crystalline based on the upon the type of constituent particle occupying the latest state, the type of binding force, and the various crystalline solid are classified into the following type. First is ionic crystalline. In this crystalline, the constituent particle occupying the latest point are positive negative ions. These ions are together have the strong electrostatic force of attraction, and some of the important characteristics of these crystalline are as flow. Because of the strong electrostatic force of attraction exists among the ion, they have a very high melting and boiling point. They have second the good conductivity. The good conductivity of electricity in is the molten state or in a solution. but not in the crystalline state where the ion are not free to move. Third is they are soluble in polar solvent but insoluble in non-polar solvent. Because of the strong electrostatic force of attraction, the ion are closely packed and hence the ionic solution I had hard. However, they have crystal. Because of this stability of crystal depend upon the preservation of geometrical pattern. Second is molecular crystal. The constituent particle occupying the lattice point in this case are the molecule, and the intermolecular force holding the molecule together in a crystal lattice are the van der Waals force. In the case of polar molecule, the dipole direction as shown in figure 3.4. In the case of non-polar solvent molecules H2Cl2 CH4, the van der Waals force on the London depression force. These forces are believed to be arise due to the momentary dipole produced as a result of distortion of the electron called W1 molecule, which is produce an induced dipole in another molecule as given in figure 3.4b. They are already been discussed in unit second. The main characteristic of the molecular crystal as follow. First is as a van der Waals forces are much weaker than the electrostatic force exist in the ionic crystal. The molecular crystal are soft and have a low melting and boiling point. Second, they do not conduct the electricity of the solid liquid state, or in the solution there are no ion present. Third, they are less soluble in water and more soluble in non-polar solvent and polar molecular liquid act as a solvent of the ionic compound. Fourth is dipole attraction are the strong than the London force, and therefore no polar molecule crystal generally have the higher melting point and boiling point than the crystal and non-polar molecule of comparably molecular size and shape. Third, the atomic or network or the covalent crystal. In this crystal, the lattice points are occupied by any atom with linked together by a network of covalent bond to form a gratin molecule. One of the most common example of the crystalline is this type of the diamond. This and that of the diamond, in which the carbon atom are linked together by a covalent bond to give the three-dimensional structure as given in figure 3.5. The substance of this type of have the very high melting point, boiling point, and point low validity, and the extremely hard because of the large number of covalent bonds that have to be broken to destroy the crystal structure. They further have no conducting of the electricity. Fourth is metallic crystal. This crystal consists of the positive charged metal ion and occupying used in crystallography is face of the surface of a metal called the face of crystal, as line along which the adjacent face of the crystal insert is called as, and the form a set of similar face of the crystal in the form is called a form, and the faces of all these given make the crystal angle and which other with the other faces. John, 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 because of the regular shape of the crystal face are found to be occur his set meet to be parallel edge and will be meet in all parallel edges if the plane of the face are extend, and such a face is known as John crystal habit. The external shape of the crystal is called the crystal habit. The internal face is the angle between the adjacent face of the crystal is called interfacial angle. Steno's law of convenience of the interfacial angles. The crystal of the substance are obtained by the cooling of the liquid or the solution of that substance. The size of the crystal depend upon the rate of cooling. If the cooling is carried out slowly, the crystal of the large size are obtained because of the particle get sufficient time to arrange themselves in a proper position. Similarly, if it is found that the shape of the crystal of a substance also depend upon the condition under which the crystallization take place, and in the presence of and absence of any of the other substance, etc. For example, shape of the crystal of a particular substance is shown in figure 3.7. However, in spite of the different size and shape of a crystal of a same substance, the flowing regular is observed. The angle between the corresponding faces is called interfacial angle of a crystal of a particular substance. are always the same independent of the other of the shape and size of the crystal. This is the law of constancy of interfacial angle. The instrument used to measurement of the interfacial angle is called a geometer. A very simple and common form of the geometer is contact geometer. It has been flat and a flat arm protect to on the center of the straight portion of the semicircular scale shown in figure 3.8. At the angle of their position, the two arms can be claimed to drive the angle with the help of screw and they tucks. The two arms are similar to the pair of scissors, and the crystal is placed between the two arms such that it joined the force are touching the arm. The arm are then clamped and the ankle between the arm is ready for the scale. Above technology is useful only when the crystal are large in size and with the clear cut faces. However, for more precious work and for small crystal, an optical instrument called refractive geometer is used or the best in the X-ray geometer. Further, it found that the form and the shape of the crystal of the substance are rather depend upon the condition under the crystallization take place in the absence and presence of any other substance, etc. For example, sodium chloride grow as a cube from water solution but as an octahedral from 15% urea solution. A large variety of the shape of the crystal substance has been observed. One of their tempered to classify the variety and show the shape on the basis. Since such classification is based upon the symmetrical exhibited by the crystal and their internal surface structure. In the next session, we shall therefore discuss the element of the symmetry posed by the crystal and the molecule. Element of symmetry. The crystal of the various substance possesses a various flowing different type of the symmetries. First is center of symmetry. It is defined as an imaginary point with the crystal such that at it has passing through the point intersecting the position opposite faces of the crystal are equal in distance. The center symmetry is also called the center inversion because of it crystal or the molecule R is inverted through the center of symmetry. It result equivalent to the original and hence indistinguishable from the original one. And for example, the center of inversion of a few are given below. Second is plane of symmetry. It is defined as an imaginary plane passing through the crystal such that it divides the crystal into two parts in such a way that one of the part is the mirror image of another, and the plane of the symmetry are therefore called the mirror plane. Third is rotational axis of the symmetry. The rotation axis of symmetry, or the simple called the axis of symmetry, is defined as an imaginary line passing through the crystal such that when the crystal of is rotating about 360 degrees, it is appearance will occur with in one correct regulation. The axis is called two-fold axis of symmetry or the dial axis. Similarly, the other possibility found for the similar pairs is one complete revolution are twice and four times are the six times. The corresponding axes for these are third fold and four-folded and six-folded axis symmetry. The above type of rotation which lead to equivalent configuration which are considered as is called a proper rotation, and the axis is called proper rotation axis. Further, it may be joined out to we have been two-fold, three-fold, four-fold, and six-fold axis rotation. We get the five-fold and seven, eight, and higher fold axis of rotation as will be explained later in the section 3.13. The rotation and reflection axis of the symmetry. When the rotation of molecule or the crystal about an n-fold axis of a proper rotation is followed by the reflection through a plane of perpendicular to the axis. The axis is called n-fold rotation reflective axis, and the configuration obtained is not confident but it is anisomorous. For example, rotation followed by the reflection of symmetry of that like a manual Numerical 7 is shown in figure 3.10. Rotation inversion axis of symmetry. When the rotation of the molecule over the crystal is followed by the inversion through the center symmetry, the axis is called the n-fold rotation inversion axis, and the new configuration is obtained is not congruent but is enantiomorphic is as in above cases. For example, rotation followed by the inversion of the numerically 7 represent in figure 3.11. Corresponding to the n-fold axis, there is rotation reflected axis represent as an n-fold axis, and the rotation inversion axis represent the n-fold axis. The above two type of rotation reflection, rotation inversion will be give the an isomorphic configuration. These are called improper rotation, and the axis is called improper rotation axis. The various type of symmetry is discussed above are collectively called the element symmetry, and the operation involved like rotation, reflection, inversion are called symmetrical operation. Further, it may be mentioned that whereas a crystal may be have many plane of symmetry, many axes of the symmetry, but it cannot never have a more than one center of symmetry. In the cases of these, may be no center of symmetry at all because of different development of the opposite phase of the different crystallization. Law of symmetry. The crystal of the particular substance always possesses the same element of symmetry. This is a law called law of symmetry. For example, a cubic crystal always possesses a 23 different type of element of the symmetry. First, A is rectangular plane symmetry, B is diagonal plane symmetry is of 6 type, the four-fold axis of symmetry 3 type, three-fold axis of symmetry is 4 type, and the two type of symmetry is 6. The center symmetry is of 1. As an example of each type of symmetry possessed by the cube in figure 3.12. Crystallography axis and axis rotation ratio. As already mentioned, as a crystal is a regular arrangement of constituent particle, the point observed by this particle with the crystal are called the lattice point. Any plane passing through a large number of lattice points is called crystal plane, and a very large number of the set of parallel plane exists with the crystal. Some of these set of the parallel plate present with the crystal are shown in figure 3.13. The planes of surface of the crystal are called the face of crystal. In order to describe the relative direction and operation of the faces are also called the plane present with the crystal, and three stable axes are chosen which meet at a point say O, and these axes may be selected in a way of depending upon the symmetry of the crystal. However, the best choice is usually the line and cosquant the axis into three lines mutually at a right angle to each other. The three lines thus selected meet at a point called the crystallography axis, and now the stable plane is called standard and unit plane is selected which cut all the crystallography axes. For example, suppose the three axes represent OX, OY, OZ, and the unit plane cut these axes A, B, C respectively, and making the intercept of OA is equal to A, OB is equal to B, and OC is equal to C. The ratio of A ratio B ratio C is called the axis ratio, and these axis ratio may be defined as the ratio of intercept which made by the unit plane of the crystallography axis. It is important to note that the actual length of the intercept ABC depend upon the position of the origin O, but the ratio is constant, and therefore the ratio which is significant is decreasing the shape of the crystal, and further it convergent to the right B as a unit. For the copper sulfate crystal, this axis is A ratio B ratio C is 0.5715 ratio 1 ratio 0.5575. The angle between these axes opposite to the intercept ABC represent the alpha, gamma, and beta respectively. These angles are same as the interfacial angle if the axes are chosen as a line constituting with the parallel to the edge of a principal axis of the crystal. These angle together with the axis ratio are called the element of crystal. Higgs law of rotation indicates If the intercept of any other plane of the face of the crystal on the three axes is measured, the following generalization is observed, which is called the law of rotation indicates the intercept made by the plane or the face of the crystal on the crystallography axis are either first same as those of the unit plane, second is simple whole number multiply of these two u of the plane unit plane, and third is one to intercept may be infinite if the plane or the face are parallel to one another of the axis. If the plane or the faces does not cut one out the two axes, for example, the intercept made by the L, M, N, A, B, A, 2A, 2B, 3C are simply whole number of the multiple of the unit cell against the considered in the case of cubes. Suppose a region of O of the crystallography like at a center of the symmetry and the axis is OX, OY, OZ are parallel to the as shown in figure 3.14. Suppose the axis of OX cut these faces A, B, C, D at a point L. Similarly, suppose the axis of OY, OZ cut the faces M at M and N are shown in figure 3.14. If the LMN is taken as a unit plane, the intercept made by the unit plane on the this axis OL, OM, ON, the faces ABCD cut these axes at L and make the same intercept as the made by the unit plane, but it can be done not by cut the y-axis and z-axis at all, because these two axes are parallel to the faces. In another word, the intercept made by the faces abcd on x y-axis z-axis are infinite. In general, if the face pqr make the intercept pqr on the three axes and the intercept made by these unit cell abc, then have a p is equal to na, p is equal to n dash b, and r is equal to n dash double dash c, where n dash and n double dash are the simple whole number of the sum of out of the days may be infinite. Identification and destination of the crystal plane and the faces. First, the term of vagress indicates if the face make intercept NA, NB, NC on the crystallography axis, the face are represented by the N dash n and n double dash. The number n dash and n double dash are used by representing the faces called the faces and indicates, and however this method represent the face is cut by the user. In term of measure indices, it is common to make the reciprocal of the number n dash n double dash and then the multiple then of the smallest number, so to express all the reciprocal as integrator. The integrator tux obtained is called the Mr. Indicator, and tux the Mr. Indicator of a plane or a feature may be defined as the reciprocal of the coefficient of the intercept expressed as the integer, or the Mr. Integer may be defined as the integer which give the ratio of the intercept of the unit cell to those the given plane or the faces expressed as integer. Observably, the measured integers of a given plane or the face inversely proportional to the intercept of that plane and the face of crystallography axis. Example: first, in figure 3.30, in the intercept of the faces LMN is equal to 2a, 2b, and 3c. And the reciprocal of the coefficient of a b c is equal to 1 by 2, 1 by 2, 1 by 3, and the LCM of this is 2, 2, 3 is equal to 6, and the multiple reciprocal of 6 where we have 3, 3, 2, and this measure indication of the facial element in figure 13, 3.13, and these faces represent the 332. And second, the intercept made by the unit plane called are A, B, C, and the coefficient by of these intercept are called 1, 2, 1, 1, 1, and hence the unit cell plane is represented as 1, 1, 1. And since third, in the same some face does not cut the same axis at all, the intercept on this axis is taken as infinite in X plane in the section 3.19 and the figure 3.14. For example, suppose the face make the intercept 2 its 3b on the axis and the y-intercept does not cut the z-axis at all. The intercept will be 283b and infinite, and the x y axis respectively does not cut the z axis at all, and the intercept may be 283b infinite, and these reciprocal of the coefficient is 1 by 2, 1 by 3, and 1 and 0. LCM of these is by 2 or 3 is equal to 6, and the multiple is 6, and the missing indicate will be 320, and the face of the represent as 320. Similarly, if the face make the intercept A on the axis and does not cut the y axis and z axis at all, the mission indication will be 100, and it may be represented as 100. Fourth, if the sum indicator meet the facial is negative, the face is cut by the axis in when the extend in the opposite direction. The it represent by putting the bar over it, and the example is in the figure 3.14. Intercept made by the EFGH on the axis is A, and this faces does not cut the y axis z axis at all, and hence these faces are represented as 100. The measure indicates of the faces of Q, refreshing in which the origin of this crystallography axis is the center of symmetry of the cube, and follow the method to as explained in third and fourth. About this fact, faces of cube in term of the measure indication may be represented as 100, 101, 001, 100, and 1010 slash and 001. All these faces are said to be belong to the same form represent as 100. Further, it is important to note that whether the crystalline there is large number of plane in different direction, and the direction intercept of these crystal plane are also designed in term of measure indices, and taking a simple case is represent the latest point in one plane of the crystal, and taking the c axis as an perpendicular on the page. Some set of plane that are parallel to the c axis as shown in figure 3.15. In fact, these are an is an infinite number of the set of the plane. The face and the crystal plane are maybe designed in the general way as shown. As usually, let ABC represent the length axis direction of these units as shown in figure 3.16. Let us plane ABC. We make the intercept of OA, the OC on the axis, and then the ratio of the intercept to these length of the unit cell will be OA by A, OB by B, and OC by C. The reciprocal of these length ratio will be AO A by OA, B by OB, and C by OC. The set of these axes is so selected, and these ratio come out of the smaller integral whole number, and the small integral is represented as HKL, and the measure indicates the plane are shown in the represent as we have main returned. For example, the plane ABC intercept 1 by 3A, 3 by 4B, 1 by 3C, and the coefficient unit cell is 1 by 3, 3 by 4, 1 by 2. Reciprocal of 3, 4 by 3, 2 is clear the fraction multiplied by the 3, we get the 946 as a mission indication of the plane ABC. Distance of separation between HKL plane. Within the crystal, there are a large number of equal specialized parallel planes which with the measure indicates one of these are supposed to be through the origin. The perpendicular distance of plane from the origin is represented by DHKL, which will be may be the interplanar distance, and the adjacent parallel planar. This may be expressed in terms of this unit distance ABC, and the measure indicates HKL as follow. So the square and addition of the equation we get cos A O B D plus cos B O D plus cos 2 C O D is equal to D at D square H square by A square plus D square K square by B squared plus D square L square by C square if the x's are chosen are or orthogonal alpha is equal to beta is equal to gamma is equal to 90 degree. The LH of the above equation may be equal to infinite and hence alternative it may be derived in the simple manner as follow. Consider the two-dimensional lattice or is orthogonal system in which A is not equal to B and the intercept of the plane AB are the mission indicator of HKL on the axis and the B axis will be A H B K and represent respectively. Let OP is perpendicular on AB and first writing the angle OAB and similarly triangle of OP and OAB extending these in three-dimensional and calculating the distance of separation plane from the DHKL value of lattice which is orthogonal axis for the NH and KL and planes. The this implies that if the mission indicator is multiplied by a factor and then the separation between the plane and reduced by that factor. For example, the distance between 2 to 0 plane is half that of 110 plane as shown in figure 3.18. Note first the plane divided by A into the H equal part, B into the K equal part and C into the L equal part. The smaller the value of H in the plane is more nearly axis to the A axis and same is true in the K and the B axis, L and the C axis. Keeping in the mind the reciprocal of the measure of the lower H value means that intercept at a larger distance of X is a lower value of K means a large intercept of the B and so on. When the H is equal to 0, the plane intercept of A is at the infinite that of plane are parallel to the A axis and similarly plane are parallel to the B axis and the plane is parallel to the C axis. Crystal system. If the element of the symmetry are distributed theoretically around a single plane is in a space, it's found that 32 different arrangements are possible, and these different type of arrangement of the element of the symmetry about a single point are called the crystal class and the crystallographic or a point group. Further, maybe point group may be have the same axis ratio angle. The 5 point around the 32 have the alpha is equal to beta is equal to gamma is equal to 90 degree. A ratio, B ratio, C ratio is equal to 1 ratio 1 ratio 1 ratio and where A is equal to B is equal to C and all this corresponding to the cubic shape. If the in this way the 32 different has been grouped into the 7 type on the basis of the axis ratio and angle. Since the external geometry of the crystal depend upon the axis ratio and the angle, this implies on the basis of the external geometry of the crystal they may be classified into 7 type of which are called the crystallographic system. The name of this system along with the axis characteristic maximum plane and axis of symmetry, the number of point group belong to each system is example of the each system as shown in table 3.33. The shape of the virus crystal as shown later in figure 3.21. Isoformic and polymerization. The certain crystalline substances which may be similar chemical composition, sodium phosphate, sodium acetate, are found to be possess a same crystal shape. The phenomena is known as isomorphism, and the substances are called isomorphous. These are the many substances which exist in more than one crystal form, which are found under the different condition of temperature and pressure. This phenomena is called polyphonization. For example, the carbon in the crystallization form we are graphite and diamond. The calcium carbonate exists into two crystalline forms called the chalite and aragonite. The polymorphism exists by the element is called the allotropous, and the temperature at which the at which one crystalline form changes into the another is called the transition temperature, space lattice, and unit cell. So far, we have been discussed about only the external shape of the crystal. On studying the external structure of the crystal, it found that the particle constitute the crystalline substance are arranged in a regular fashion with the crystal in three-dimensional space. For example, the arrangement of particles for a cubic crystal is shown in figure 3.19. The regular arrangement of the point constituting the particle in a three-dimensional space with the crystal is called the space lattice or crystal lattice. If a bigger size crystal is broken into more and more intimately, a stage is reached when we get a smallest possible crystal. If the broken further, it break to give a constant particle, the ion atom and a molecule. For example, if a bigger cubic crystal is broken, the smallest crystal obtained will be small cube is represented by a thick line above. This small cubic crystal has all the elements of the symmetry as posed by the bigger cube crystal. Moreover, it is evident that the complete radical lattice has been obtained by the re- repetition of this smallest unit in different direction. The smallest portion of the complete space lattice which have the all the element of the symmetry and which are repeated over again and again in different direction produce the complete space of lattice is called unit cells. The situation may be compared with the other thick wall made by of the brick, whereas a brick is similar to the unit cell and the wall of the complete space lattice. It may be noted, may be point that it is the regular arrangement of the point that constitute the space lattice and not that of the line joined them. The line has been drawn just to indicate the regular interpretation more clearly to describe the position of a point. Further, in order that the unit cell may be described completely, we should be know the dimension of the unit cell, vice versa, ABC, and the angle alpha, beta, gamma between them, as shown figure 3.19. It may be reciprocal. Then the section of 3.6 is may be mentioned about that has only two-fold, three-fold, four-fold, five-fold axis of rotation. We do not have the five-fold, seven-fold, eight-fold, or higher fold of rotation. It observed due to the fact that the most of the essential requirement of the lattice is that it should be built up the repetition of the unit, the faces of the axis unit cell touching the face of the surrounding unit cell without leaving the gap in between them. Such a close packing is possible if one object of two-fold, three-fold, four-fold, or six-fold of axis between but in not possible in the case of an object of 5 or 7 fold, 8 fold, or higher of the symmetry. An example of these is illustrated in the figure 3.20 and for the object have the six-fold of the symmetry and five-fold of the axis confining of to the two dimension for the sake of the simplicity, and the situation is similar to the fact that of the impossible of to the foil and with the regular pentagonal heptagonal without leaving the gap in the tiling. Griffith's lattice. In the space of lattice considered above, it is assumed that there are the point only at the corner of the unit cell. The detailed study of the internal structure of fabric has shown in that point may be present not only at the corner of the unit cell but at the center of the faces or within the body of the unit cell. The given Give it the 14 different type of lattice corresponding to the 7 crystallography system already described. The 14 type of the lattice is called Previs lattice, and the description of these lattice in the given table is 3.4 and the shape shown in the figure is 3.21. On the next page, the term simple faces, center faces, and centered body center are referred under simple when the points are represented only at the corner of the unit cell. Second is face centered when the addition points are at the corner and their points are present at the center of each faces of unit cell. Third is end centered when it in addition to the point at the corner, there are the point represent at the center on the end of the faces of unit cell. Fourth is body center. If when Addition to the point at the corner, there is one point present within the body of each unit cell, simple unit cell. When the points are present only at the corner of the unit cell, this is called primitive unit cell, and these other type of unit cell are non-primitive unit cell. The number of units per cell in n is equal to expression n is equal to nc by 8 plus nf by 2 n plus ni. Nc is the number of points present on the corner of the unit cell. Nh is the number of points present on the face of the unit cell. Ni is the point represent in the interfere of the unit cell. The expression from the following fact that the point present on the corner is shaped by the 8 unit cell. Each point present on the face is shared by the 2 unit cell, and the point present on the interior is shared by the no other unit cell. Space group. It has been already been discussed in 3.11 that theoretical that 32 different type way of the arrangement of the element of the symmetry about a point. This different arrangement is called point group. However, in the complete space lattice, because of the regular repetition of the pattern in the three-dimensional space of two additional symmetry is called a glide plane, and the cruise axis become the possible. The detailed discussion of these new element of the symmetry is belong to the scope of a present book. However, it is mentioned to maintain these because of this additional element of symmetry. The number of arrangements possible by the element of symmetry about a point outlet is become manifold equal to 230, and the 230 possible arrangement of the element of the symmetry about a lattice are called space group, and the split of these spaces are corresponding to different crystal systems as shown in figure 3.5 on the next page. X-ray diffraction by a crystal to study the internal structure. The external shape of the crystal has been with the help of the optical microscope on the basis of the crystalline workers flying into the sound system already discussed, and the internal structure escaped of each atom where the unit cell is going to be studied unit discovered by the X-ray. Using the X-ray, the diffraction study with these carry out by the understanding the structure of crystal or a brief described below. Lewis method. Max von Lewis in the 1912 is a variable section if a variable section consists of a large number of atoms and arranged in ordered manner that the atomic plane. Max Lewis in 1912 may be variable suggestion that if the crystal consists of large number of atoms and arranged in order manner and the atomic plane in a crystal where the separation of distance between these are nearly the same magnitude as the wavelength of X-ray, there will be X-ray are around stack a crystal, and the ray will be penetrated with the crystal will be saturated by the electron of the atom and ion of the crystal. The ray reflect from the different layer of the atom due to the wave nature will be undergo the interference to produce the diffraction pattern, just as it happened in the case of light falling through a gravitating constant. A large number of close space line in another word the crystal should act as a three-dimensional grating of the X-ray, and this idea of the when Sol put on to experiment test tube and found to be true. In the Lewis method, the continuous separation of X-ray will be widely ranged wavelength is used, and the purpose of this is that to list some of the radiation wavelength is used, and the purpose of to do this is list the radiation would be proper wavelength to undergo the interference, and these understood as to shown in figure 3.22, and the Lewis diagram of the NaCl is shown in figure 3.22b. Such diagram confirm the defined arrangement of the element in a crystal. However, the interception to each of the exact arrangement of atom with the crystal is difficult. A simple method and is always has been put forward by the WH Beveridge as discussed below. Baggs method. The Baggs method for a study of internal structure of crystal is based on the Baggs equation, which was derived as follows. A crystal has been considered to be made up of the number of parallel evidently atomic planes as represented in the line of x and x dash, y and y dash, and z and dash, z dash as in figure 3.23. Suppose a beam of light x-rays insect on a crystal at angle theta, and a part of this beam may be reflected at a point B along with the BC. On the other hand, the X-ray like the D, F, and GH may be penetrate on the crystal and reflect by the atom in which the atomic plane YYZ ZZ as shown in figure 3.5. The evidence as compared to the AB array like the B DE may be travel in a longer distance equal to the JEK order to impulse out of the crystal of BZ and KZ are perpendicular drawn in the line of DE and IF respectively. The reflective beam of the BCEF undergo the interference with the each other if the refracted ray are in the phase, and in the reflected ray the crystal day reference into other and intensity of the refractive ray is maximum. On the other hand, the if the refracted ray out of the phase, the intensity of reflective beam is very low. If the photography plate is placed to receive the reflected ray and diffraction pattern is obtained. It is observed that in order that the reflective ray BC and EF may be in the phase and the extra distance JEK traveled by the ray DEF should be integral multiple of wavelength lambda of the X-ray. The distance of JEK is equal to n lambda, where n is the integer 1, 2, 3, 4, etc. If the d is the distance between the successive atomic plane, it observed from the figure 3.23, that is jk is equal to ek equal to d sine theta. jk is equal to 2d sine theta. We put the equation first figure, the 2d sine theta is equal to L lambda. This is called Baggs equation. It is give us a condition under which the refractive ray may have the maximum intensity using the monochromatic X-ray. Lambda is constant after the particular crystal. When a particular face is facing the X-ray, d is constant and hence d will be integer only for the certain value of the angle theta, and thus gradually increasing the value of theta. A number of positions are observed corresponding to the n is equal to 1, 2, 3, 4, etc., where the refractive beam of the have a maximum intensity. For another value of theta lying between the refractive beam will be have the maximum or less than the maximum. Thus, the diffraction pattern will be obtained in such a way that the various corresponding n is equal to 1, 2, 3, etc. And these are respectively called diffraction maximum of the first order, second order, third order, etc. The measurement of the angle theta at the first maxima occur so that n is equal to 1. We can know that the wavelength lambda is equal to x is used, where the value of d is calculated using the equation. The apparatus used by the Beveridge for studying the internal structure of crystal for the measurement of the intensity of the refractive beam, the corresponding to different value of the theta, is called Beveridge X-ray separatometer is known in the figure 3.24. X-ray was generated in the X-ray tube A. Ducts are made monochromatic by bypassing them through the observation screen B, and there will be passed through the lead side L to obtain the fine beam. This beam was then allowed to fold some particular phase of the angle large crystal C, which is mounted to on a turntable T, and the turntable is moved on a circular scale as the refractive beam is passed into the ionization chamber T, and this is connected by the electromotor. The ionization chamber on is also moved on the circular scale as an independent of the turntable T, and the chamber containing some easily ionizable such as the sulfur dioxide. Greater is the intensity of refractive beam, greater is the ionization produced in the gas, and larger is the reading on the electrometer. When the crystal face is rotated by rotating the turntable, the diffraction of the refractive beam changes and reverts the refractive beam into the ionization chamber. Every time the ionization chamber is rotated through the double bond, and the angle through the crystal face is rotated, and these are plot the angle corresponding to the first and second third of maxima are noted, and the value of d will be calculated by the Bagrias equation. Evidence for in the favor of Bagrias equation. For the sodium chloride, the crystal are the faces in the first, second, third maxima at an angle of 5.9, 11.85, 11.15 by using the X-ray produce the paradomic target, and since these are also 0.103, 0.205, 0.31 to very nearly the ratio 1 ratio 2 ratio 3, and the proof that the first, second, third maxima have the occur the n is equal to 1 to 3 respectively. Hence the correctness of the Beveridge equation is confined. Smaller the hump of on the left of the maxima is due to the beta radiation accumulation of X-ray is used. Calculation for the Beveridge equation. According to the Beveridge equation, 2d is sine theta is equal to nd, where the particle phase is known as the angle theta at which the first order of diffraction is obtained, and also known the wavelength of X used in the interplanar space will be calculated. Further, the cube system value of d is given by the d HKL is equal to a by under the root h square plus k square plus l square. Known the value of the d calculated from equation second above. The length a of the edge of a cube unit cell is calculated. Alternative, knowing the interplanar specific d HKL, we can be calculate from the equation third. If the edge of the unit cell is known, knowing the value of theta at a particular first order diffraction maximum is the equation obtained first and can be used to calculate the wavelength lambda of the X-ray, and also having the lambda and d upon the equation first, and theta will be calculated from the using the value, and the length a of the edge of the cube unit cell is obtained by the various equation, and the studying the using equation second third we can check the calculation from the above alternative method based on the knowledge of the density of the crystal and the type of lattice of a unit cell. Taking the example of an NaCl crystal, which is a face center cubic, it is Na plus 4Cl negative ion per cell. If the 4 NaCl unit cell, the mass of the unit cell is equal to mass of the 4 unit cell, where is equal to 4 into mass of the 1 unit cell. 4 is 4 into m by n node. If the density of the NaCl crystal, volume of the unit cell is equal to 4 into m by lambda by the n node. The value of the edge A determined is found to agree well with the calculation of Beveridge method, and further to give the support of Beveridge X-ray diffraction method. This method relates to support to the structure of an ACL to the conserved and used to in calculation above. Determination the type of cubic lattice. There are the three type of cubic lattice, namely simple, phase and face center, body center. Possible the crystal plane through the lattice point. There are of three type along with the 3.36. There are the million degrees are given below. Simple cubic lattice is 100, 110, 113. Phase cubic lattice is 200, 220, 111. The body center cube lattice is 200, 100, 22. The interplanar distance of the three type of cube lattice can be calculated by using the formula d HKL is equal to a by under the root h square k square l square. These values are easily given by this figure. The table of interplanar distance of these type of lattice are shown below. To see which type of cubic center of the crystal is belong, the reflection from the diffraction plane of the study the angle to determine at which these refractions take place. The interplanar distance of each set of the plane calculated using the Bedrich equation d is equal to n lambda by 2 sine theta. The ratio of interplanar distance of the three planes is then calculated and compared with the theoretical calculation ratio for the different type of cubic lattice given above. Determination of NaCl, KCl and CSCl from the external geometry. It is found using the optical microscope. All the three type has been found it to be below the cubic system. In the NaCl crystal, the first order reflection from the three faces of the crystal are found to be occur at 5.19 degree, 8.4 degree and 5.2 degree respectively. Applying the Bedrich equation 2d sin theta is equal to n lambda. It is evident that the ratio of these three interplanar spacing will be in ratio of 1 by sin theta, where the value of n and lambda are constant for the given experiment. Thus, we can use the ratio will be in the ratio of 9.7 ratio 6.65 ratio 10.99. As per the ratio is closer to the face center and hence the crystal of the NaCl has a face center, cubic center, producing texturally in the same as the above. It found that KCl has been face center, cubic center, whereas CCl has body center, cubic structure. Powder method. This is a simple method for studying the X-ray of the diffraction of a crystal. It is developed by the Degree and Duskert in 1961 and independently by the Hugel in the 1917. In the Bedrich method, a simple large crystal is required and more it has been rotated about a suitable axis where this method the sample is taken in a powder form in a small thin walled glass tube and no rotation is required. Of course, the tube is rotated to ensure that the crystalline is powdered and a randomly originated. A beam of monochromatic X-ray is focused on the small sample and a circular photographic film is placed around as it's shown in the figure 3.27. And since the powder, the crystal plane of diffraction, smaller crystals are rotating at a particular angle to the beam, and there will be always some crystal which have the proper orientation to produce diffraction from all the planes symmetrically. In the principle of the set of HCl give rise to a diffraction cone to originate from the powder, and thus a large number of coincident cones are produced due to the refraction from diffraction set of a plane and the certifying the very low. Each cone of the meet the photographic film at a point. Two lines at equal distance from the bridge center spot, and these are the large number of lines from the center spot. For the dividends of the theta, the refractive beam make the 2 theta with the diffraction of the incident beam as shown in figure 3.27. An appropriate idea for the general diffraction pattern of the produced may be shown as in figure 3.28. After getting the X-ray, the diffraction pattern of the powder, and the next is inducing of the line, assigning the middle relation to the plane responsible for producing this line. These are proper distance. By taking the half of the distance from these two lines on the either side of the center, if the radius of the film is r, the circumference is 2 pi r corresponding to the scattering angle of 360, impulse that the 2 theta by the 360 is equal to x by 2 pi r. And thus the theta is calculated, and knowing the theta interplanar spacing, we can calculate using the Bedrich equation where 2d sin theta is equal to n lambda. Diffraction pattern obtained by the powder method are characteristic of the solid substance. The position of the line of the photography depend upon the spacing between the crystal plane and hence on the type of crystal. This is a reason that the method is quite obtained from the quantitative as well as a quantitative analysis to identify the estimate pure substance and the mixture. Moreover, this method is much easier than the simple Crystal method. Excellent diffraction pattern of cubic lattice. The cubic system is simplest for the older system because all the length of the unit cell are equal and each angle is equal to 90 degree. For any set of plane with the miscellaneous indicates the interplanar distance can be calculated using the expression DHKL is equal to A by under the root H square K square plus L square. According to the Gauss equation, the Gaussian refraction, the first order diffraction is equal to sine theta is equal to lambda by 2 DHKL. Substituting the value as DHKL from the equation first, we get that theta sine square theta is equal to lambda square by 4a square into h square plus k square plus l square. For the given cubic system, for the particular X-ray, X-ray use A and lambda constant and hence is equal to lambda square by 4a square is constant, and putting the constant to a, the equation 4 becomes that sine square theta is equal to h square plus k square plus l square into a. The substituting the value of induce of the plane present in the three type of cubic lattice, the value of theta in the term of sine square theta can be calculated using the predicate line that would be obtained on the photography film. This can be explained below of the three cubic lattice. First is primitive. Using equation first, the internal value of the indicates HKL. The DHKL may be have the value given in table 3.30 3.6 below, which have been A by under the root 7. By missing the 7 cannot be obtained from the h square plus k square plus l square, where HKL are integer and corresponding value of the sine square theta are also given in a same table. The value of sine square theta is equal to 7a and also not be possible. Thus, we can consider that the powder diffraction pattern of the primitive cubic lattice will consist of 6 equal space lines below by a gap and then again a set of line and so on. Second is face-centered cubic lattice. This type of lattice is obtained from the refraction in a phase take place only from the plane of rod HKL are either odd or all even. Carry out by the calculation as above. The value of the D HKL and the sine square theta is given in the table 3.7 below. Thus, the line will be observed at angle as shown in figure table above. Third is center cubic lattice. For this lattice, it is observed that the diffraction are not observed from the plane of which is odd, and carrying out the calculation as before, the value of DHKL and the sine square theta are given in table 3.8 below. Thus, the line will be observed at an angle shown in the table above. It can be noted that all the them will be equal space. The diffraction pattern of the three type of the cubic lattice as explained above may be represented together as follow. This type of cubic lattice can be determined by observing the axis diffraction pattern produced from the simple and the missing line extent are greater in the assigned type of lattice, and knowing the value of these plane from the which the reflection take place corresponding to the which the line can be diffraction is obtained, and the corresponding value of sine square theta and hence the sine square theta which a line in the diffraction pattern is obtained. The corresponding value of sine square theta and hence the sine theta and the edge of the cubic lattice will be calculated using the equation third, and hence we can return as a is equal to lambda by 2 sine theta into the under the root h square plus k square plus l square. For the reflection for any plane and the corresponding sine theta value of the a always be come out to be constant. Crystal structure of NaCl, KCl and CSCl. The chlorine lattice display a by 2 along with the edge of the cube, and this structure is further supported by the fact that it is a unit cell containing the 4 NaCl plus 4 Cl ions, keeping in the mind the contribution made by the corner, face, edge, center and the border center. KCl is also face center cubic lattice, and similarly to the NaCl in which The Na plus atom have been replaced by the K atom in the CsCl is found to be have a body center cubic lattice as shown in the figure 3.31. In the fact, it has two simple cubic lattice, one of the cesium atom and another chlorine atom, which are interlocked together to the pseudo body center lattice. This structure is further supported by the fact that a unit cell containing the Cs plus and one Cl ion. It is interesting to point out that the NaCl and the KCl have a similar structure, and their diffraction pattern of the ensemble different can be explained on the basis of the fact that the X-ray is saturated by the electron and diffraction. Different atom and ion have contained a different number of electron, and hence this saturation strength are different. Greater the number of electrons, greater is the saturating strength. Moreover, the value of the X-ray saturated by the atom interfere. The value saturated by the cation depend upon the origination of the ion, and the reflection may be in the phase and out of the phase. In the case of NaCl, the number of electron in the Na plus is less than that of Cl ion, and therefore the saturating strength are different. But in the case of KCl, both the K plus Cl ion contain the same number of electrons, and their saturating strength are equivalent. So when we out of the phase, the saturating strength of Na plus and Cl negative ion do not cancel out the complete. Therefore, in the case of KCl plus and NaCl negative ion, the cancellation is complete, and the ion in the KCl therefore are look very similar and interest of appearance to the phase center cubic. The powder diffraction pattern obtained is similar to that of the primitive cubic cell unit. In fact, the relative position of the atom and the ion in the crystal is determined by studying the intersetting of the line obtained in the X-ray produced the refraction photography. Co-originated the coordinate of the lattice in the different type of cubic structure. First is for a face center cubic structure, such NaCl taking the Na plus at the corner and the origin of that it can be origin coordinate are 001A. The coordinate of NaCl ion is in the face center will be half 0, second is 0 half 0 half. The coordinate of the Cl present at the edge centered will be half 0 half 0 half. The coordinate of Cl in the representative body center will be half. For the simple cubic unit cell, the corresponding lattice point at a corner is 000 1 and 111. For the body center, the cubic lattice at a corner have a coordination number second, and above which that of the point the body center are half. For a cubic lattice, the distance between the 2 point of coordinate x1 y1 z1 and x2 y2 z2 can be calculated by using the formula d is equal to under the root x1 minus x2 का whole square plus y1 minus y2 का whole square plus z1 minus z2 का whole square into a. Crystal structure of calcium fluoride. In the fluoride, each Ca plus ion is surrounded by the 8 F negative ion. Give a body center cubic arrangement of the F negative around the Ca plus ion, and since there are twice as given in the F negative ion as the Ca plus ion, the coordination number of the both the ion is different, and the 4 Ca plus ion are tetrahedral arrangement of the each F negative ion. The coordinate number are therefore 8 4 is called the 8-4 arrangement. The fluoride structure is found to be the ratio of 0.73 or the above. An alternative description of the structure is that the Ca plus ion face from the face centered cubic arrangement, and the Ca2 plus ion are too smaller to touch each other, so that the structure does not closely pack. And however, the structure is related to the close packing arrangement, since the Ca plus ion occur only the same relative position for a cubic close packed structure, and the F negative ion occur at all the tetrahedral hole.